recorded, but that's fine. Okay, so then moving on to what we're actually doing. If you click on 13C and open it up, comes to here. Our goal today is students will compare and contrast the characteristic properties of ionic and covalent compounds by drawing visual notes of 2 different articles. This is a 2-day assignment. So this is due tomorrow at midnight. But it is really 2 days worth of work, and you'll be coming back tomorrow and we'll be going through the second bit. So anywho, our basic idea is that there are 2 types of bonds that we're learning about, ionic and covalent. We have been drawing ionic bonds. Later next week, we'll draw covalent bonds. However, first we're going to go over the characteristic differences between these 2 bonds. So today, we're going to read this link, this article. As we read, you need to doodle on a piece of paper to represent what you are reading as best as you can. You're going to love it. Think of this as visual notes. I'm going to show some examples. However, try to limit yourself to only 10 words on your paper. Get creative with your images. Get the colored pencils, markers, or crayons out, or pen/pencils work as well. So I will show you the examples, and I'll give you a minute to go get a piece of paper and whatnot. Oh, I didn't need to open this. I already have it open. So let me come over here. These are my examples. So this is what visual notes are. So basically, I'm going to show you an example, then I'm going to show you why they're like beneficial. So this is the one I scrolled too much. This is the example that I like. Corn casserole, right? Big letters here. You know what this is talking about. You look at this, you glance at this, and you kind of know what goes in corn's casserole. Onion, cheese, crackers, corn, chilies, eggs. Great. You're set. You're golden. Okay. So this is like a visual representation of the recipe. So what we're going to be doing is reading the article, and you are going to be doodling a visual representation of the article. So why do we do this? Visual metaphors, and this is kind of an example, but this is more words than what I'm picturing, but we'll see. Visual metaphors allow brains to fill in gaps. It simplifies it. It enables connection, raises attention. It helps in sense making. It helps you make sense of what's going on, helps with clarity. So it's very beneficial. There's a lot of different parts. So hopefully this is part of our being more efficient learners. We'll see how it works. And then other things, you can like use arrows and shapes, and it's called sketch noting, but I like calling them doodling. But so this could be like more of kind of what I'm picturing, like this stick image, a sun, a flower, whatever. So this topic was like the rainforest, and maybe they read an article about the rainforest and then kind of drew like what it was to like represent what they read. Who knows? I don't know. I was just picking images of these doodles. So hopefully that kind of makes sense. The color ones are kind of cool. I kind of like them, but if you're black and white, that is perfectly good with me as well. So I'm giving you 60 seconds right now to go get a piece of paper and a pen, pencil, writing utensil. I don't know. Utensil, writing utensil. So go do that. I will wait. Okay, that was a minute. Hopefully you have something to write on and write with. And we are going to begin. So I'm gonna like kind of help and work us through it today. We'll see about tomorrow. But so this is the article that we are reading. I'm going to click on it, open it up. So this is called Ionic Compound Properties Explained. So we are going over ionic bonds. These are ionic compounds, and over their characteristics. So at the top of your sheet, maybe in the big bold letters, like bring some attention to it, you write the word ionic, because that is like the main label. You could do like ionic characteristics, something like that to bring your attention. This is what my topic is. This is what we're talking about. So definitely should probably have something related to that. I'm gonna read this first bit, and then I'll give you a moment of time. So we have an ionic bond is formed when there is a large electronegativity difference between the elements participating in the bond. The greater the difference, the stronger the attraction between positive ion and negative ion. So we don't really know what electronegativity means at this point, but that's okay. Focus on the words we do know. So we know Positive ion is like when you drew those ions and they had a positive charge, and negative ions was when you drew those little dot structures and then made them, get 8 or 0 or whatever, and then they had a negative charge. So on your sheet, you hopefully have our label or a space for the label, and then maybe you could write like positive, negative, and then we have the word attraction. What could represent, and this one I'm talking through a little more, I won't talk through all of them, but like what could represent attraction? Maybe like, I don't know, a heart or multiple hearts, or maybe you have like two people holding hands, and maybe you have like a positive sign above one and a negative sign above the other to show like the two different parts are like attracted to each other, which is what our ionic bond is. So like just trying to kind of help you out with the starting of the doodling. Something like that is ideal. I'll read this and then I'll give you 60 seconds as well to like finish your title and hopefully a little bit. Just like you could also draw, kind of what we were drawing last week, like with the electrons and whatever, and 8 and 0 and them next to each other type of deal. But anywho, this one says, properties shared by ionic compounds. The properties of ionic compounds relate to how strongly the positive and negative ions attract each other in an ionic bond. Ionic compounds also exhibit the following properties. So that's what we're getting to is the properties, but I'm going to give you 60 seconds. Again, I would do like, your plus and your minus, because that is kind of our key deal with ionic compounds. And definitely you need that word ionic big and bold and on there real clear. So I'm going to start this. I'm going to stop talking. What are we writing? You are writing what you want. But your goal is to visually represent the article. So your goal is to visually represent the article. And what we have so far is the title, which is, don't write this whole thing. Maybe just do ionic characteristics or something, or just ionic. And then we know this thing about the positives and the negatives. So how can you represent that? Okay. So hopefully we drew that. Next up is we're going to read the next paragraph. So this is our first characteristics. It's called they form crystals. I am going to have one of you read it. I will give you 10 seconds for someone to volunteer. If nobody volunteers to read it, then I'll pick somebody. Could still be you, but I'll wait 10 seconds. If anybody wants to unmute their
I'll read it.
Okay, cool. Thank you.
Wait, right there where it says they form crystals?
Yep, this. Yep.
Wait.
What?
Can you hear me? It's because it keeps freezing.
No, I can hear you.
Okay. Ionic compounds form crystal
lattices.
Lattices rather than
amorphous. You got it.
Amorphous solids. Although molecular compounds form crystals, they frequently take other forms. Plus, molecular crystals typically are softer than ionic crystals. At an atomic level, an ionic crystal is a regular structure with the cation and cation and ionic alternating with each other and forming a three-dimensional structure based largely on the smaller ion, evenly filling in the gaps between the larger ion.
Love it. Thank you so much. Really appreciate it. Okay, a lot of big words there. So I have a short clip to kind of show like what the heck is this even talking about. So this is the first little one, and stick with me. And again, our goal is as we're reading this or as you're watching this, kind of be drawing things like, oh, that's what that is. Okay, I'm going to draw this to represent that type of deal. So this is structures of ionic solids. This is like what the crystal, this is like the lattice crystal type word thing.
Ionic solids have a definite crystalline structure. In this model,
and this is that structure. So like this blocky looking structure, that is what that is.
You see a sodium and chlorine atom, and they're attached to opposite types of atoms. So if this is sodium, that's a chlorine, that's a chlorine, that's a chlorine. If you look inside here, that is attached to 6 atoms of the opposite type. If you hammer on this,
I'm gonna just stop it there. So basically, they're always attached to what is opposite of what it is. And then I do want to show you. So this would be just Googling image quick ionic compounds crystal. Like, what does that mean? What is this looking like? So you have these blocky looking things, right? Which is showing how the ions are combining together to make this form. And then also you can think about it in terms of like, okay, a literal little like crystal looking thing. You got some different rock type images here. So let me see if there's anything else I wanted to say about that. Right. So no. So this is like the form that this is the shape they form, these crystal lattices. So you could maybe write down that word, but then maybe draw something to like let you know what that looks like. And then the alternating with the cation and anion, that's alternating with a plus charge and a minus charge. And that is where that is. So I'm going to, again, I'll give it like 60. Yeah, I'll do 60 seconds again. And draw what you want. I'm going to leave it on the article page. So maybe reference that, be like, oh, I could draw that to help show this. Okay, that's our minute timer. So on to our next little paragraph. Again, hopefully you have like some images or something to represent that. And go big or go home. Doesn't need to be small. And also you can have multiple, like, oh, this could show it or this could show it type of deal. Okay, this is our next paragraph here. I'll give it 10 seconds. Does somebody else want to volunteer? Thank you very much to Alexa for volunteering for the first one, but I'll see, give it 10, and if not, I will pick on somebody. Let's go with Saul. Saul, are you around? Can you unmute your mic and can you read this highlighted blue section for me, please? And I picked Saul because I think Saul's friends with Alexa. That was my reasoning. So the rest of Alexa's
list. Yes, I will. Hurry up.
So the rest of Alexa's little group better watch out. Because you're next. Maybe he's not here. Alexa, text him. Maybe he is.
I got it.
Okay, cool.
They have high melting points and high boiling points. High temperatures are required to overcome the attraction between the positive and negative ions in ionic compounds. Therefore, a lot of energy is required to melt ionic compounds or cause them to boil.
Thank you. Okay, so as we're thinking about this and reading this, like, what can you draw to show that ionic compounds have high melting points and high boiling points? And then I have a very brief clip. Don't even know if this really helps, but we'll see. Here we are.
So we have our anions and cations, which are our positive and negative ions. They're surrounding each other and they form an ionic lattice. Now, the thing that gives ionic compounds a high melting point is our strong electrostatic attraction between those cations and anions. That's going to get you 2 marks in an exam. The third and final mark is for turning around and saying that lots of energy is needed to break those bonds, to break that strong electrostatic attraction. Therefore, they have a high melting point.
Okay, so this is like the reason why these things have a high melting point, is because these are very attracted to each other. So this positive and this negative, this is a strong electrostatic attraction between the positive and the negative. So it requires a lot of energy, so that would be like more heat, and that's a higher boiling point. That's why we have a high melting point and high boiling point in ionic compounds. So when you're drawing, think what could represent something that's a really high melting point and high boiling point, like something, I don't know, hot, maybe something like that, or maybe multiple things in order to show that. And energy, you could, to show that lots of energy is required, like maybe, I don't know, draw a little kid jumping on a trampoline, like that is a lot of energy, right? I would last like 30 seconds. I'm like, okay, I'm winded. But little kids can do this for like 10 minutes. I don't know, show something with a lot of energy to show like, okay, it requires a lot in order to break that positive and that negative. I will set another timer here. We'll do 45 seconds. So this is your time to doodle this bit. Okay, we're skipping this, and we are doing this. They're hard and brittle one. Any volunteers? I'll give it 10 seconds. What if like the whole time I didn't know we were doodling? Well, at least you're figuring it out now, and you can catch up. So your goal, and everybody's goal with this, is to be doodling, sorry, not drawing, because we're not that fancy. Unless you are, then great, love it. But is to be representing this article in terms of like one of these things, right? So you got your title, and then you got like little things to represent these different things, or multiple little things, right? You could do like a bunch of different things to represent, like heat, maybe fire, and a thermometer, and things that are hot, the sun, type of deal. Anyways, I'm gonna keep going. We can't get sidetracked. They're hard and brittle. Did I have a volunteer? Calling Kevin. Kevin left. Oh, Kevin's back. Kevin, don't think I didn't see you leave. Because I actually was gonna call on Kevin, and then I was like, oh, he's not here anymore. Kevin, can you unmute your mic, please?
Yo.
Can you read this sentence starting with they're hard and brittle? Sorry, this paragraph.
Ionic crystals are hard because the positive and negative ions are strongly attract to each other and difficult to separate. However, when pressure is applied to an ionic crystal, then ions of like charge may be forced closer to each other. Those, how is that,
electrostatic.
Repulsion can be enough to split the crystal, which is why the ionic solids are brittle.
Awesome job. You sound a little sickly now, but great job. This is where, what am I doing for this one? Oh, I'm showing this next little bit. Okay, they are hard and brittle. Again, you should be trying to draw this. This is a helpful little video in case you're like, I don't even know what that means.
To show one of the properties of ionic solids, which is the brittleness. This is a model of sodium chloride. The sodium ions are the little blue ones. The chloride ions are the larger green ones. So we've got positive and negative ions
all adjacent to each other. Very strong ionic attractions there, whole network of them. What we're going to show is the brittleness of ionic compounds. So I'm going to hit this along the edge of the piece of wood here. 1, 2. And as that happens, notice that an entire circle.
Okay, we see that he's gonna do it in slow motion. I'll play that once. Oh, if my internet goes out, right? Okay, good. I think this one's slow-mo. Okay, that was not slow. Oh, there it is. Okay, there's slow-mo, and then he's about to explain it here.
All right, so we're down to this little cube. So when I push this down, you can now see that the 2 chloride ions and the 2 sodium ions are lined up with each other. That's a repelling force. It wants to push away. And so as a result, this thing goes flying away, and you get the 2 separate pieces right there. So there we go. There you go.
Okay, so just to reiterate that, so why this is known as this brittle thing is because then when it shifts and it moves down, like if you hit it with like a hammer or something, you knock on it, whatever, it shifts down, and now the positive charges are next to each other. So because those are next to each other now, they're like, oh, heck no. And then it breaks off type of deal because those are not attracted. Those repel each other. So that is why it's brittle. But then like on top and bottom, those are still attracted to it. But since it shifted, then it kind of knocks off type of a deal. So hopefully that helped a little bit. And yeah, when thinking about brittle, if you are like, well, what do I draw for this? You could maybe draw this like force, like how he hit it. It's a sharp blow. Like that's usually what happens. It's like something gets hit and then it splits type of deal. That like the crystal cracks. So you could do that. You could draw something to represent brittle, like maybe one of my favorite little things to eat sometimes. Not always. I'm not always in the mood for it, but like you could draw some peanut brittle, right, to represent that ionic compounds characteristics is that they are brittle. You could draw peanut brittle with a hammer hitting it if you're super fancy, or do what you want. Okay. Let me see here though. I'm not going to give you time to draw on this one only because hopefully you did already, or the doodling part might be your homework because I want to get through the rest of it. So let's go with Bridget. Can you unmute your mic, please? And can you actually read both of these? I know there's 2, but we're kind of going to combine them because we're short on time.
Wait, what do I read again?
The highlighted blue parts.
Okay, they conduct electricity when they are dissolved in water. When ionic compounds are dissolved in water, the dissociated,
Yep,
right? Ions are free to conduct electric charge throughout the solution. Molten,
Mhm.
Is that it? Ionic compounds also conduct electricity. They're good insulators, although they conduct in molten form or in, what does that say?
Aqueous
Solution. Ionic solids do not conduct electricity very well because the ions are bound so tightly to each other.
Awesome. Love it. Thank you. So the first thing we're going to talk about is this dissolved. When ionic compounds are dissolved in water, the dissociated ions are free. So what does this mean? I am going to show you a video.
When an ionic substance, such as sodium chloride, is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become...
Okay, a lot of fancy words in there, but basically this dissociation, that fancy word, is like the peeling back, the like removal of the ions. So it's the ions become separated from each other. And do notice, like, these things want to be together. It's minuses and pluses. They are attracted. They like each other. They're like, we want to stay together. But the water molecules, these red things, are more. Seriously?
Solution.
Okay. So basically, I got chopped up a little bit there, but hopefully you can follow along with the rest of this video. So basically, the water molecules come and they kind of peel this back, and this is the dissociation of the ions. So now these ions are free and they're moving around in the water because they're not like attracted to each other anymore. So now we have positive and negative charges in the water. Um and so then I'm going to play this video to show as to how they conduct electricity and why they're good insulators. So let me skip to here.
We know from various lines of experimental evidence that solid sodium chloride consists of an ordered three-dimensional array of sodium and chloride ions. Solid sodium chloride is not a conductor of electricity. The ions of the ionic lattice are held in place by the strong ionic interactions in the solid and therefore are not free to move under the influence of the electric field.
Okay, so notice the light bulb is not lit up because we have this solid NaCl. So this solid NaCl is just like this block, right? And when it's in the block, the positives and negatives, when it's in the block, the positives and negatives don't have room to flow. Maybe not room. They don't have like the freedom to flow because they're attracted to each other. So they're sticking together. But keep watching.
Influence of the electric field. When sodium chloride is dissolved in water, it forms a solution of separated sodium and chloride ions. The presence of ions in the solution is responsible for the fact that the solution is a conductor of electricity. Substances such as sodium chloride that exist in aqueous solution entirely or nearly entirely as ions are called strong electrolytes. By contrast, an
Okay, that's enough of that. So basically, since the ions are split in this NaCl solution, so meaning they dissolve because the water like took them and then like peeled them back, they broke the electrostatic force. This is why it conducts electricity in water, is because of the dissociation of the ions. So back to this. So they do conduct electricity when they are dissolved in water, and that was kind of like what it looked like. And they are good insulators because when they are solids, ionic solids do not conduct electricity. They are insulators because the ions are bound so tightly together. So that is that. You should have like a drawing of this whole thing, like a bunch of different little doodles and images. And then tomorrow we'll do the covalent one.